density. Okay, so I have some really nice objects here. We'll start off with. So this is a little wood cube, like that. You can measure the volume, but I don't really need to. I can measure the mass. I mean, I don't really need to. I have this really old scale here. This is 15 grams-ish. Okay, so look at that. Now look at this. This is some type of plastic. Maybe it's, I don't know. But you'll notice it's the same size, approximately the same size, right? Same size cube. Now if I find its mass, 18.6 grams. So these have the same volume, but this has a greater mass. Okay, so there's something different about these, and we have to realize when we talk about big, it's bigger or the same size. There's two things. There's volume, which is how much space it takes up, and it's mass, and those are different things. So let's look at all of these cubes. Check that out. So I've arranged these cubes. They're all the same size. Wood. I guess that's Teflon. I don't really know. I'm gonna say Teflon. And this is like plexiglass or something. And that's ABS plastic, maybe? I don't know. Aluminum? Steel or iron, I'm not sure. I think this is copper. And I think this is brass. But nonetheless, this is the heaviest at like 100 and, let's see, 148 grams. Okay, so these are all increasing in mass, but they're the same volume. Okay, now let's take this cube. So if I find the mass, it's an aluminum cube. I don't know if you can see, it says 48.6. Now I take this one. This is the plastic, okay? The ABS plastic. Notice that it is the same area, but a larger height. So the volume of this is bigger. I put it on the scale. 47.9. So it's approximately the same mass, but in order to have the same mass, this has to be larger volume. Okay, so these have the same volume, but different masses. And I could do this one. This one's even bigger, but if I found the mass of it, the mass is the same. And then here again. So these, all of these have the same mass approximately, but the volume gets bigger and bigger and bigger. So what is it, a property where these all have the same volume but different mass, these all have the same mass but different volume? And then I could take something like these. These all have different masses and different volumes, but they have something in common, and that is the density. The density of the material tells you the ratio of mass to volume, and it's constant for the material that it's made of. So I'm going to take these, let's see, I have 5 objects. I have these 5 pieces of, they're all made of the same material. I'm going to measure the mass, and I'm going to calculate the volume, and we're going to make a graph of mass versus volume and find the density. That's what we're going to do. Okay, so let's start off with the smallest one, this one. So I'm going to find its mass. I'm going to do this live. If it takes all day, it's going to take all day. I need my marker. Okay, so the mass of that one is 17. Let's just say 17. I'll round off. So I have a chart here. 17 grams. And now let's find the volume. Okay, so I'm going to take, I should have picked a ruler that wasn't broken. So this is 3.8 centimeters by 3.8 centimeters by 0.7. So I'm going to take my calculator. On clear. 3.8 times 3.8 times 0.7. 10.1 cubic centimeters. Got it? Okay. Next object. I'm not sure if I'm going to, let's do this one. This one, see, this one's a little bit thicker. I'm going to assume it's the same dimensions on the base. It's close. So I'm not going to remeasure that. So this has a mass of 29.4. And the thickness of it is, let's see, 3.8 times 3.8 times, what's that? This one I said was, oh, that one, I'd measured the wrong one. This other one was 0.3. Okay, so let's write this as 10.1. And let's calculate that one. 3.8 times 3.8 times 0.3. 4.3. Okay, so I've gotten those two. Now let's do this one. $54.4. And the thickness is 1.3-ish. 3.8 times 3.8 times 1.3. 18.7. Okay, so I'm done with this guy. Okay, now this one is different dimensions, so that's fine. 40, oh, it's got the same mass as this, so we only have 4 data points in. Okay, 47.8, and the volume of this is 5 by 2.6 by 1.3. So I have 5 times 1.3 by 2.6. Is that what I said? Yeah. 16.9. Okay, so there's my data. And you'll notice this one, it has a lower volume than one before, but also a lower mass. So the ones that have the smallest mass have the smallest volume too. Okay, so now we're going to make a graph. You could just calculate mass divided by volume, but that's not nearly as much fun as making a graph. So let's make a graph of, since I know that density is mass divided by volume. So let's put mass over here and volume. Right there. I've already made some lines on there. So my mass goes from 17 to 47. So if I go 10, 20, 30, 40, 50, that'd be enough. But if I could go 10, 20, 40, 60, I could do that. Okay, right. So that's the first one, and then I could do the volume. It's going to go up to 16. So if I go 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so I can just go 1 cubic centimeter per thing right there. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. So the first data point I have is the mass is 17, so that's right here. And the volume is 4. So 4. Right there. The next one, the volume is 10, so 0.1, and the mass is 29. So right here. The next one is I'm going to go the 16.9, so it's 16, 17, and 47. So here's 47. That's over a little bit. Yeah. And the last one is 18.7, so that's 16, 17, 18, and 57. So that's 54. There's my 4 data points. That's not a data point. Okay, so now how do we find the density? I'm gonna find the best fit line here. So I'm going to draw a line that kind of comes close to all of these. And now the slope is going to be the change in mass over the change in volume, and this is equal to the density. So I just need to find the slope of this line. So let's just say at this point, it's kind of hard to read. Let's say okay, so that's going to be the change in mass is going to be equal to 50, let's say it's going to be 50 minus 6 over the change in volume, which is going to be 16, 17, 18, 19, 20 minus 0. So it's going to be 50 minus 6 is 44 over 20. Okay, so if I calculate that, sorry for my handwriting, 44 divided by 20. I get 2.2 grams per cubic centimeter. And that is the density. That's the density of aluminum. If I did a different material, I would get a different density. You know, I could even take something like this. As long as it's aluminum, I could calculate the volume of this and the mass divided by volume would be the same thing. But that is your density. It's the ratio of mass divided by volume. This straight line shows that the ratio of mass and volume is constant for that material. And that is density. Oh, the actual density of aluminum, I think it's 2.7 grams per cubic centimeter. But I did this really rough. I didn't even use graph paper. So I think that's pretty good.